AP Chem Topic 3.2, Properties of Solids. We're not really focusing on the types of solids in this video. We've done that in previous videos. This is on the properties and what about the solids leads them to have those properties. But in order to have that conversation in a way that makes it easy to understand, let me do a quick review. Ionic solids are held together by the attraction between the positive and negative ions. They self-assemble into highly ordered lattices because of that. Metallic solids are held together by a free-flowing sea of electrons. The nucleus and some of the core electrons are fixed in place, and then valence electrons dissociate and can move freely about them. A molecular solid is held together strictly by intermolecular forces that exist between the particles in the substance, and then a network covalent solid is held together by a network of covalent bonds between the atoms. Okay, so let's talk about conductivity first. So a substance is conductive if it has mobile charges. So for this reason, an ionic solid is not conductive. So remember that in the ionic solid, these charges are fixed in place so that it's not conductive. But as soon as you turn it into a liquid or you dissolve it, it becomes conductive because then these charges can move. A metallic solid will always be conductive because it has these free-flowing sea of electrons, so the electrons can conduct. A covalent solid and a network covalent solid will not be conductive because their electrons are fixed in place in both cases. Next, we'll look at vapor pressure. Vapor pressure is impacted by the intermolecular forces and their strengths. So if you're comparing two substances, something with a low or lower vapor pressure is going to have stronger IMFs. That is because the intermolecular forces hold those particles together more strongly. Therefore, it requires more energy to overcome them for the particles to escape the surface of your liquid and turn into a gas. So that would be ionic solids or network covalent solids, for example. A high vapor pressure would be due to weaker intermolecular forces because those forces are holding those particles together with less strength, and therefore it is easier for those particles to overcome that intermolecular force at that temperature. So we would expect that to be something like a molecular solid. Now, or molecular substance. Often you will have to compare vapor pressure of two liquids that are both molecular, and so in that case you would likely look at the strength of the London dispersion forces or whether or not hydrogen bonds are present or the strength of a dipole-dipole. Boiling and melting points are reasoned in a similar way to vapor pressure. They are, again, the result of the IMF strength. So think about, again, what is happening when you have a phase change. So when you have a phase change, you're overcoming the interparticle forces to separate the particles from each other, and they also start moving faster. Okay, so they basically spread out. So if they have a lower boiling or melting point, that means that the IMFs are weaker, and they are therefore easier to overcome at lower temperatures. So that would be something like a molecular substance, but again, I would expect you to have to compare two molecular substances. If you have a higher boiling point or melting point, that means that the IMFs are stronger, and it requires a higher temperature to overcome them. You have to put more energy into the system. Rigidity and hardness is usually based on how ordered the lattice or the network is, or actually the presence of a lattice or a network. So for example, something that would be hard or rigid is an ionic solid or a network covalent solid because they have that, if I go back to my pictures here, they have that lattice in the case of an ionic, or the network of covalent bonds and network covalent. So these are very ordered, and that makes them very hard. Also, these attractions are very strong. This is a covalent bonds. This is essentially ionic bond. And so those are harder to overcome as well. So that's what makes them hard and rigid, and also contributes to other properties of ionic and network covalent. Things that are soft and malleable are metallic or molecular because, again, there's not that rigidity. Now, an important footnote for metallic: forming an alloy can make a metal harder, especially if you form an interstitial alloy, and that's one reason we choose to form alloys. Finally, in this section, we have a little bit on polymers. So polymers are an entire field of chemistry that you can choose to go into if you wish, but we're just going to take the very briefest scratch of the surface. So if this were a monomer, then a polymer is where several monomers self-assemble together into this repeating structure that comes together to be a larger structure. And so we've got lots of examples of those in real life: rubber, plastic, fabrics, for example. And then we've also got biological examples of those as well: DNA, proteins, carbohydrates. So if we think about DNA for a minute, DNA would be a polymer, the nucleic acids would be the monomers, and then this is held together in a three-dimensional way by intermolecular forces. And that's true for all of these. So a lot of these they all assemble into larger samples. And then the molecules themselves might be held together by bonds, like covalent bonds, but then you also end up with a three-dimensional structure that can be due to either bonds or the presence of intermolecular forces, like in the case of DNA, which is famously held together by hydrogen bonds. So there you go. That is it for properties of solids.